You wouldn't be crushed by a black hole. That's the image most people have. Falling in, being compressed, squeezed into nothing by overwhelming gravity. It's wrong. What actually happens is stranger and, in a certain sense, more disturbing. You'd be stretched, pulled lengthwise into a thin strand of matter, compressed from the sides, elongated along the direction of fall, until the atomic bonds holding you together can no longer resist the differential forces pulling you apart. Physicists call this spaghettification, not as a joke, as an accurate physical description of the process. I'm Paul Dirac. Let's understand exactly why this happens, what it feels like from inside and outside, and where the physics eventually runs out of answers. The mechanism isn't simply gravity is strong. That's too vague. The mechanism is that gravity is not the same everywhere, and the difference in gravity across a finite-sized object is what does the damage. Gravity from any massive body follows an inverse square law. It gets weaker with distance. The surface of Earth pulls your feet harder than your head because your feet are closer to Earth's center. On Earth, this difference is about 1 part in a million. You don't feel it. But the difference exists, and it has a name, the tidal force. Tidal forces are responsible for ocean tides. The side of Earth facing the Moon is about 12,000 kilometers closer to the Moon than the side facing away. The Moon pulls the near side harder than it pulls Earth's center, and pulls the center harder than the far side. Earth stretches slightly in the direction of the Moon. The oceans, being fluid, bulge both towards the Moon and away from it. 2 high tides per day. Same physics, differential gravitational pull across a finite-sized object. Scale this up. Now put a human body in free fall towards a black hole. Feet pointing towards the singularity, head pointing away. The gravity at your feet is greater than the gravity at your head. The tidal force, the difference, tries to accelerate your feet faster than your head. In your own reference frame, it's as though something is pulling your feet away from the rest of you and pushing your head away in the opposite direction. You're being stretched along the direction of fall. And simultaneously, from the sides, the tidal force compresses you inward. The gravity pulling your left side and the gravity pulling your right side are both pointing toward the singularity, which means they're converging. They're squeezing you toward the center line of your trajectory, stretched lengthwise, compressed from the sides. The forces increase as you fall deeper, as the gravity gradient steepens. Eventually, the differential forces exceed what atomic bonds can resist. Your body is drawn apart, unmade not by crushing, but by differential pulling, becoming something long and thin and no longer recognizably you. The name is accurate. This is spaghettification. Now here's something that genuinely surprises people. The size of the black hole changes the experience entirely. A stellar mass black hole, formed when a massive star collapses, typically a few to a few tens of solar masses, has a Schwarzschild radius of kilometers. The event horizon is small, the singularity is close, and critically, the gravity gradient near the event horizon is steep. The difference in gravitational pull between 2 points a meter apart near a stellar mass black hole's horizon is enormous. You would be spaghettified before you even crossed the event horizon. At a distance of perhaps thousands of kilometers, you'd start to feel the tidal forces. You'd never make it inside intact. Now consider a supermassive black hole. Sagittarius A star, the black hole at the center of our own galaxy, has a mass of about 4 million suns. Its Schwarzschild radius is about 12 million kilometers. M87's central black hole, the one photographed by the Event Horizon Telescope in 2019, is 6.5 billion solar masses. Its event horizon spans a region larger than our entire solar system. For these monsters, the tidal force at the event horizon is surprisingly gentle. The gravity is still extreme, but the gradient, the difference between nearby points, is much smaller because the event horizon is so far from the singularity. You could cross the event horizon of M87's black hole without experiencing anything locally dramatic. No alarm, no barrier, just crossing a geometric boundary while floating freely. Spaghettification would come later, deep inside, where the distances from the singularity become small enough for the gradient to become catastrophic again. Bigger black hole, paradoxically, means gentler entry. Let me be precise about what the event horizon actually is, because it's almost universally misunderstood. It's not a physical surface. There's no wall, no membrane, no boundary you could detect locally as you crossed it. It's a geometric boundary, the surface inside which no path through space-time, including paths taken by light, leads outward. Inside the event horizon, space-time is curved so severely that all trajectories lead toward the singularity, not tend toward. All trajectories, without exception, end at the singularity. In the mathematics of the Schwarzschild solution, the exact solution to Einstein's field equations describing a non-rotating black hole, inside the event horizon, the radial coordinate switches character from a spatial dimension to a temporal one. The singularity isn't a place in space you can choose to avoid. It's a moment in time that all infalling matter inevitably reaches. The way tomorrow is inevitable for you right now. Inside a black hole, the singularity is your inevitable future. You can no more avoid it by changing direction than you can avoid Tuesday by changing your physical location. From outside the black hole, watching you fall in, an observer would see something strange. They'd see you slow down as you approach the horizon. Your image would redshift, shifting to longer, redder wavelengths as your light climbed against the intense gravity. You'd appear to freeze, dimming and reddening, never quite reaching the horizon, fading from view over an apparently infinite time. This is real. It's not an illusion. In the external observer's coordinates, you genuinely, asymptotically approach the horizon and never cross it. But from your own reference frame, falling freely, feeling no local force, you're in free fall, gravity is locally equivalent to weightlessness, you cross the horizon without any special local experience for a large enough black hole. You can't know the moment of crossing. There's no marker. And once inside, you have a finite amount of proper time, your personal experience time, before the singularity. How much depends on the mass. For a stellar mass black hole, microseconds. For Sagittarius A star, perhaps minutes. For M87's black hole, potentially hours of personal time, falling toward a singularity that grows increasingly inevitable. Spaghettification isn't just a thought experiment. We've watched it happen to stars. When a star wanders too close to a supermassive black hole at the center of a galaxy, the tidal forces rip it apart. This is called a tidal disruption event, a TDE. The star is stretched and shredded, its material forming a long stream. Some of this debris falls onto the black hole, spiraling inward, heating to extreme temperatures and radiating intensely across multiple wavelengths. Some is ejected at high velocity. The result is a bright flare, sometimes visible across billions of light years, that rises and fades over weeks to months. These events are now detected regularly by sky survey telescopes. AT2019QIZ, a tidal disruption event observed in 2019, was caught early enough that astronomers could watch the flare build as the stellar debris began falling onto the black hole. They could measure the rate at which material was accreting, infer the mass of the star being disrupted, and track the spaghettification process through its electromagnetic signature. Not a thought experiment, an observation. Spaghettification is a phenomenon we can watch from billions of light years away. And now, the singularity. At the end of every infalling trajectory, inside every black hole, at the center of the Schwarzschild geometry, the singularity. In the simplest mathematical description, a point of infinite density, infinite space-time curvature. General relativity's equations, when applied here, produce results that no physics can correspond to. Infinities. The singularity is not a place in space. It's a moment in time, a future moment for all infalling matter, as certain as the end of a clock that's winding down. And it's where spaghettification reaches its completion, where the tidal forces become literally infinite in the classical solution, and where matter is crushed to zero volume. But here's what I want to say precisely. The singularity is a sign that general relativity is incomplete. Not that there's a genuine infinity in nature. Every time a physical theory produces infinities at a boundary, it's telling you it's been pushed beyond its domain of validity, that a deeper theory is needed. The singularity of a black hole is the place where general relativity admits it doesn't know what happens. What actually occurs at the scales where quantum effects become relevant, at the Planck scale, 10 to the power of minus 35 meters, requires a theory of quantum gravity we don't yet possess. The singularity is an edge of our knowledge written in mathematics. And this opens the deepest question. When you fall into a black hole, when you're spaghettified and absorbed, what happens to the information that constituted you? Not just your atoms, but the specific quantum state of every particle, the information that made you, you, and not something else. In classical general relativity, the singularity destroys this information. It's simply gone. But quantum mechanics says information cannot be destroyed. It must be conserved somewhere in some form. This isn't a matter of preference. It's a foundational principle of quantum theory, and violating it would break quantum mechanics structurally. This contradiction is the black hole information paradox. Hawking showed in 1974 that black holes emit thermal radiation, Hawking radiation, due to quantum effects near the event horizon, and that they eventually evaporate completely. If the radiation is purely thermal, containing no information about what fell in, then the information is destroyed when the black hole evaporates. Quantum mechanics violated. Current theoretical work, the island formula, the page curve calculation, recent insights from holography and quantum gravity, suggests that information does survive, encoded in subtle correlations in the Hawking radiation. But the precise mechanism by which information escapes the interior of a black hole without violating causality remains unresolved. It's one of the central problems of theoretical physics today. Spaghettification, then, is not just a dramatic physical process. It's the entrance to the deepest problem at the boundary of our two best theories of reality. Your body, stretched to a strand, carries quantum information about your state, information that, in some sense, the universe is not permitted to lose. What happens to that information is a question general relativity and quantum mechanics answer differently. Resolving that disagreement requires physics we don't yet have. The black hole stretches you like pasta, and then, at the deepest level of what we understand, it asks a question about the nature of information and reality that we haven't yet been able to answer. I find that a remarkable thing to learn from a word that sounds like a dinner order.